my name is Jason Harlow. Welcome to my V office hour. I'm going to go over my solution for Physics 132 F, Fall 2010, Test 1, Problem 4 from version 1. This is based on Chapter 20 material from Knight. This is transverse waves on a string. It's got a little bit of tension and mass on a pulley, so a little bit of review material from previous chapters as well. First, let's carefully read through the question. A 2.0 meter long string with a mass of 4.0 grams is tied to a wall at one end, stretched horizontally to a pulley 1.5 meters away from the wall, then tied to a hanging mass M as shown. When you pluck the string, sending a traveling pulse down the string, it travels at speed v equals 35 meters per second. What is the mass M? And there's a selection of numbers there from 0.007 kilograms all the way up to 3.3 kilograms. Okay, so this is a Chapter 20 problem. It's about wave motion on a string. And we have an equation there which is V is the square root of the tension divided by the mass density of the string. So we're actually given the speed of traveling pulse down the string in this problem. It's 35 meters per second, and we're asked to find capital M. So let's start by writing down equations for the tension and for the mass density of the string. Okay, so first let's label the tension in the string T sub s, which is what they do in Chapter 20. And now let's draw a free body diagram for the hanging mass. We have gravity acting down, mg, and the only other force is tension from the string pulling upwards, T sub s. So if you make a sum of the y components of the forces, the mass is in equilibrium. So the sum of f sub y's equals 0, and that's with y defined in the upward direction. It's T sub s minus m times g equals 0. So solving that for the tension is capital M times g. And here we have actually neglected the mass of the string, which is going to be something like 4 grams or maybe a quarter of that for what's hanging downwards. So hopefully the mass is much, much larger than 4 grams so that we can justify neglecting that. Keep going, the mass density of the string. So we know the tension. We also need mu sub s, the mass density, which is the mass of the string, total mass divided by the total length. That was given in the problem. The total mass was 4 grams, which is 4 times 10 to the minus 3 kilograms, divided by 2 meters long. That gives 2 times 10 to the minus 3 kilograms per meter. Continuing down the solutions, we use equation 20.1. That's the speed of transverse waves on a string equals square root of the tension divided by mu sub s. We have both of those, m times g divided by mu sub s. Solving that for capital M, we get m equals v squared times mu sub s divided by g. So it's 35 squared times 2 times 10 to the minus 3 kilograms per meter. This is all in SI units, divided by 9.8 meters per second squared. That gives a mass of 0.2 kilograms, which is answer B. So that's the answer. It's B. Now we neglected the mass of the part of the string that is hanging down below the pulley. Now the total mass of the string is 4 grams, and it's 2 meters long, and 1.5 meters of it is horizontal. So there's half a meter or 1 gram of string hanging there. So if you take this into account, you can solve it properly and get the mass is 0.249 kilograms instead of 0.25. But to two significant figures, it's the same. So the answer is still B. So we're justified in neglecting that string. My name's Jason Harlow, and I approve this message.